Hey everyone, and welcome back to the channel. Today, we're taking a trip back in time way back, to when our planet was a completely different world. Forget the blue skies and breathable air we know and love. We're journeying to early Earth, a time when the atmosphere was a toxic cocktail of gases, and the surface was a chaotic, fiery landscape. How did we get from that hostile environment to the life-sustaining planet we have today? It's an incredible story of cosmic collisions, volcanic fury, and the quiet, persistent work of the tiniest forms of life. So, buckle up, because we're about to explore the dramatic evolution of Earth's atmosphere. Let's rewind the clock about 4.5 billion years. Earth has just formed. It's a hot, molten mess, constantly bombarded by asteroids and comets left over from the solar system's creation. There's no real atmosphere to speak of, just a thin veil of hydrogen and helium, the most common gases in the early solar system. But Earth's gravity wasn't strong enough to hold on to these light gases, and the relentless solar wind, a stream of charged particles from the young sun, quickly stripped them away. This was Earth's primary, or primordial, atmosphere, and it didn't last long. Our planet was essentially a bare rock in space. So, where did our second atmosphere come from? Well, it came from inside the Earth itself. As the planet's interior churned and roiled, massive volcanoes erupted all over the surface. This period is known as the Hadean Eon, for a reason. It was truly a hellish landscape. These volcanoes weren't just spewing lava. They were outgassing, releasing a dense blanket of gases that had been trapped within the planet's mantle. This created Earth's secondary atmosphere. Now, if you were to travel back to this time, you wouldn't survive for a second. This new atmosphere was composed mainly of water, vapor, carbon dioxide, and nitrogen. But it also contained some truly nasty stuff: methane, ammonia, sulfur dioxide, and hydrogen sulfide. It would have smelled like rotten eggs and been incredibly toxic. More importantly, there was virtually no free oxygen, the gas that most life on Earth today, including us, depends on. The sky wouldn't have been blue. It likely would have been a hazy reddish-orange, due to the methane and other compounds. And the pressure. The atmospheric pressure would have been crushing, maybe 10 to 100 times what it is today, mostly because of all that carbon dioxide. But this toxic, heavy atmosphere played a crucial role. All that carbon dioxide and methane created an intense greenhouse effect. While today, we worry about too much greenhouse gas, back then, it was essential. The sun was about 30% fainter than it is now. Without this thick, heat-trapping blanket, any water on Earth would have frozen solid, and life might never have gotten started. So, this seemingly hostile atmosphere was actually setting the stage for one of the most important developments in our planet's history: the formation of oceans. As the planet gradually cooled over millions of years, the immense amount of water vapor in the atmosphere began to condense. It started to rain. And it didn't just rain for a day or a week. It rained for centuries. A global deluge that filled the planet's basins and formed the first oceans. These new oceans were incredibly important. They began to absorb some of the vast amounts of carbon dioxide from the atmosphere. This process, where atmospheric gas dissolves into the ocean, helped to slowly reduce the greenhouse effect and stabilize the climate. The oceans became a massive chemical laboratory, where dissolved minerals and atmospheric gases could interact. And it was in this primordial soup, protected from the harsh ultraviolet radiation of the sun, that life is thought to have begun. Around 3.8 billion years ago, the first simple single-celled organisms emerged. These were anaerobes, meaning they didn't need oxygen to survive. In fact, oxygen would have been poisonous to them. They thrived in this oxygen-free world, metabolizing chemicals in the water for energy. For hundreds of millions of years, this was the status quo. Life existed, but it wasn't having a major impact on the atmosphere yet. Then, everything changed. Around 2.7 to 2.4 billion years ago, a new type of microorganism evolved: Cyanobacteria. You might know them as blue-green algae. These tiny organisms were revolutionary. They developed a groundbreaking new trick: photosynthesis. They figured out how to use sunlight, water, and carbon dioxide to create their own food. And as a byproduct of this process, they released something that had never existed in significant quantities before: free oxygen. At first, this newly produced oxygen didn't build up in the atmosphere. Instead, it immediately reacted with other elements. The oceans were full of dissolved iron, and as the cyanobacteria pumped out oxygen, this iron began to rust, sinking to the seafloor and forming massive deposits we now call banded iron formations. These rock layers are like a geological timestamp, showing us exactly when oxygen started to become a thing. This event is so significant that scientists call it the Great Oxidation Event, or sometimes, the oxygen catastrophe. Why a catastrophe? Because for the anaerobic life that dominated the planet, this new oxygen-rich environment was toxic. It was a mass extinction event. the very gas that we depend on for survival, was a deadly poison to most of Earth's earliest inhabitants. The world was being terraformed by its smallest residents. As the iron in the oceans was used up, oxygen finally began to escape into the atmosphere. This had profound consequences. It reacted with the methane in the air, a potent greenhouse gas, and converted it into carbon dioxide, which is less effective at trapping heat. This reduction in the greenhouse effect is thought to have plunged the Earth into its first and longest ice age, a period known as the Huronian glaciation, where the planet may have been covered in ice from pole to polar snowball Earth. Life, however, is resilient. As the old anaerobic life forms died off or were pushed into oxygen-free pockets, new organisms evolved that could not only tolerate oxygen but actually use it to their advantage. This new process, called aerobic respiration, was far more efficient at generating energy than anaerobic methods. It allowed for the development of more complex, multicellular life. The stage was set for an explosion of biodiversity. Over the next billion years, oxygen levels continued to rise, albeit slowly and with some fluctuations. This rise in oxygen also led to the formation of the ozone layer. High in the atmosphere, oxygen molecules were struck by ultraviolet radiation from the sun, breaking them apart and reforming them as ozone, or O3. This new ozone layer acted as a protective shield, blocking most of the harmful UV radiation from reaching the surface. For the first time, life could safely move out of the protective depths of the ocean and colonize the land. This brings us to our third and current atmosphere. Today, our air is about 78% nitrogen, 21% oxygen, and about 1% argon, with trace amounts of other gases like carbon dioxide. The nitrogen has been a constant, stable presence for billions of years, but the rise of oxygen is the real game changer. This composition, perfected over billions of years, is what allowed for the evolution of plants, dinosaurs, mammals, and eventually us. The story of our atmosphere is a perfect example of how geology and biology are deeply intertwined. The planet shapes life, and life, in turn, shapes the planet. From a toxic, volcanic haze to the breathable air that sustains a vibrant biosphere, Earth's atmosphere has undergone a truly epic transformation. It is a humbling reminder that our world wasn't always so welcoming, and that its delicate balance is the result of an incredibly long and dramatic journey. Thanks for watching, and if you enjoyed this journey through deep time, don't forget to like, subscribe, and hit that notification bell for more science stories. See you next time.